Okay. So this is part one of Get to Know Your Chemistry Data Booklet because there's a lot of information that's in your data booklet that will help you revise and also be useful in paper two when you are doing the short answer for the IB exam. And so it's important that you utilize this information to minimize what you have to memorize, but also make sure you know the important parts of it because the IB is very particular about what they give you information wise so that there's still a responsibility of each student to be able to understand the material. So giving you an equation is all they give you, but they don't give you the units. They don't even tell you what each of the symbols mean and things like that. And so there is still a responsibility for students to understand the material and be able to apply those things. And so if you're just relying on the data booklet, you're going to be still susceptible to making mistakes and things like that. So let's go and get started here. Couple things. SL will be red and kind of orange, and HL will be your blue. Oops. And your violet part of the spectrum here. So that way you'll be able to differentiate for those of you that are SL versus HL material in this. But we aren't separating SL and HL content. Like we're not going to stop halfway for SL. We're going to go through the booklet in order. So there'll be sections that are just HL. Okay. First thing, your curriculum is 2016 to I think 2022 or 23. That's this cycle of chemistry. Every 7 years, the IB curriculum for science changes. They adapt things, they add things, remove things based on kind of current science and requirements and things like that for university. And so make sure that if you're happen to download a data booklet from somewhere that's not Schoology, that it's first semester 2016 and also fourth edition. The first and second edition ones are have some typos in them, and so there are some mistakes on values and things like that, and so just make sure that you're paying attention to that to make sure your cover page has that. Let's see. I was gonna say. Okay, so table of contents, fairly straightforward. We're gonna be going through today topics tables 1 through 11. So we're going to be talking about a lot of equations, constants, and then other pieces of information that they give you. Namely, there are 4 different periodic tables here. Okay, there are 4 periodic tables here, and each one gives you different amounts of information about each element, and you'll apply them in different ways. And so we'll look at that, really analyze those tables to make sure that you're using the right one to get the right information for the question at hand. Like I said before, because we're not doing any optional material and things like that, you can cross out every table from number 30 on. So 30, 31, 32, 38 are not necessary for your information. So you can cross all those pages out. In fact, if you got your copy from me, I didn't even print those copies, those pages. But when you get to the mock exam and the actual IB exam, you will be provided that entire data booklet, regardless, I believe. And so, although if the IB already said the options weren't part of it, maybe they'll take it out. But just in case, know that those last 10, 12 pages aren't useful for you. Here. Keynote here, just a reminder, paper 1 is all multiple choice, no calculator, and only a periodic table. So you see here, cannot be used for paper 1 in HL or SL material. You only get the periodic table in section 6 as part of your paper 1. In paper 2 and paper 3, which doesn't apply to us this year, you'll provided a clean data booklet like this one for your use for the exam. Okay. Questions about that?
So in some equations, such like for like the wavelength one, are we just gonna have to memorize the values for like the wavelength of light, the speed of light,
Oh
or
no,
no?
they are. That's a good question, Alejandro. They are provided to you in a table. The second table we'll look at are a lot of constants and values that you need to know. That's a good question. So we'll look at those right after we do all the equations.
Okay, thank you.
Okay, you're welcome. Okay, these first two pages are really vital for most of the calculations that you're going to be doing in the IB. Now, what the IB has generously done is they've told you what topic each of these equations pertains to. So you can see that in SL, there are only 4 equations that are relevant to you. C4 is an option, so you don't have to worry about that. But topic 1, 2, 5, and 8, those are SL topics. And so those are 4 equations that you're expected to know. Whereas higher level, you're expected to know these 12 through 19. And we're going to talk about each of these equations in our first kind of revision today. Now, PV equals energy. I don't like that this is lowercase p. To be honest with you, I think it's better as a capital P because it makes it look like the same P as in pH. But I don't know if they fixed that on the final edition, but I don't like that that's a lowercase p because pressure is capital P. But here, what we're talking about here is the ideal gas law, okay? And the ideal gas law is your pressure times volume equals your moles times gas law constant times temperature, okay? So those are your 5 different symbols in your ideal gas law here. And another important fact is knowing all the units for all of these things. And so, for example, knowing pressure is in kilopascals and volumes in decimeters cubed, or pressure could be in pascals and volume could be in meters cubed, they're the same. So if you have in kilopascals and decimeters cubed, that's the same thing as saying pascals and meters cubed, because pascals are 1,000 kilopascal. 1,000 pascals in a kilopascal, and then a meter cubed is 1,000 decimeters cubed. So it cancels out. So either way, it doesn't matter, but you want to keep those 2 units together. Your moles is mole. Your gas law constant's 8.31 joules per mole per Kelvin. Okay. And your temperature is always in Kelvin. Okay. There's really never a time in IB chemistry, or any chemistry for that matter, where you really want the temperature in Celsius. Because any calculation that you can do should be in Kelvin. Unless you're taking the difference in temperature, then that's okay. It doesn't matter if it's Celsius or Kelvin. We'll talk about that a little bit later. But really, any calculation should be in Kelvin to avoid the miscalculations, negative numbers, and the wrong scaling of temperatures and things like that. So I would just keep everything in Kelvin. Okay. Now, the ideal gas law is used for solving for one set of conditions. So like at one condition. So if you're given a pressure, and a volume, and temperature, you want to figure out how many moles of gas you have and things like that. Or you want to figure out the pressure and volume at that certain scenario, but only one condition there. Okay. The other equation that you might want to know, even though it's not provided you in here, because the IB would argue that you don't necessarily have to know the equation to be able to solve it, is the combined gas law. Okay. The combined gas law is 2 sets of conditions where you're changing pressure or volume or temperature. Okay. And that one is P1 V1 over T1 N1 is equal to P2V2 over T2N2. Now, N is usually constant because we're keeping the same moles of gas from one scenario, one condition to another. So that's why you don't usually say that, but technically it's in the equation. Okay? And so what you'll do is you'll end up changing pressure or volume or temperature and seeing how that affects the other variables in your equation. But really, you don't have to necessarily memorize this, because if you know the relationship between pressure and volume and temperature in Kelvin specifically, you could calculate this without knowing that equation, right? Because if you're going pressure versus volume and your volume goes up, you have to multiply your pressure such that your pressure goes down, because they're inversely related. So you'd multiply by the volume fraction so that you'd get a smaller number. And so we'll go into that a little bit more detail like when we kind of revise topic 1, but that is something that you want to keep in mind. Pressure and volume, all that matters is they're the same units. Okay? Temperature has to be in Kelvin. So that's the main thing for this. Questions about these two calculations and these two equations? Okay. This second equation, 2.2, this is atomic structure and essentially the wavelength and frequency of a photon, or a particle of radiation. And so here you have the speed of light is equal to wavelength times frequency. And so here, what you're really trying to show is speed of light is constant, and you'll be provided that in the data booklet in the next table. But you're really trying to show that wavelength and frequency are inversely related to each other. When wavelength goes up, frequency has to go down. When frequency goes up, wavelength has to go down. So it's that inverse relationship between wavelength and frequency you really want to focus on here. Now, speed of light is in meters per second, wavelength is in meters, and frequency is in seconds to the -1. Again, another one of those scenarios where units are really, really important. If you use this equation and you go, well, speed of light is meters per second, make sure that whatever wavelength they're giving you is in meters, because this is how, again, the IB gives you enough information, but not so much that a student that doesn't know what they're doing has the same advantage on a question as someone that does know what they're doing. So they're very, very particular about just giving you enough information to make your life easier if you know what you're doing, but not enough that you could just not know what you're doing and just throw in numbers and be able to generate the right answer. So it's this kind of push and pull with the IB about how to give you information but without giving you information. It's kind of a weird balance. Okay. Questions? Okay. This next problem, this equation, is really kind of important conceptually and also calculation-wise. It's a very popular one, and that's calorimetry. Okay. Calorimetry has to do with the change in temperature of the surroundings to measure how much heat the system is giving off. And so here you have heat is equal to mass of the solution times specific capacity times a change in temperature. And so This one again is, yeah, knowing the variables is fine, but knowing what the units are plays a key role into it. This is in joules, and this mass is in grams or kilograms, depending on your specific heat, which is usually in joules per gram degrees Celsius, and your temperature in degrees Celsius or Kelvin. So a lot of units kind of moving around here, and I'll talk to you about kind of the big pitfalls that students make. One, the difference in Celsius and Kelvin are the same. So if you go 25 degrees Celsius to 30 degrees Celsius, that's the same as 298 to 303. So the difference is still 5 degrees, and that's all you care about. So it doesn't matter if you are in Kelvin or Celsius, just don't change your difference to Kelvin. I think some kids make that mistake where they find the difference and then convert that difference to Kelvin, which isn't the intent of that. But also, you want to make sure you kind of pay attention to the units of your, I'm going to write this as grams right now just for kind of simplicity's sake. Pay attention to your units of your mass of your solution. Okay, remember, it's the mass of the water, not the mass of the metal or the mass of the salt or the mass of the compound you're putting in water. It's the water that we're calculating the energy of, because we have the specific capacity of water. We have the change of temperature of the water, so therefore that must be the mass. Students that don't understand this equation may even know Q equals mass times specific heat capacity times change of temperature, and so they just start hunting in the problem for these values. They're like, okay, where's the temperature change? Okay, that's fine. Where's my mass? There's a mass in grams. I'm going to use that. But what they forget is in these, 1 gram is equal to 1 centimeter cubed of water. So the problem never gives you the mass of the water directly. They give you the mass of water in volume and expect you to know that that's there. Another example of the IB testing to see if you really know how to use this equation. So students that just look for grams and things like that will make mistakes on using this equation. So it's giving you information but not giving you enough to be able to solve the problem outright. So it's really important that you kind of focus on that and make sure you understand that. And also, this one's a big conceptual idea. If you were here for the topic 15 energetics one, you saw how we applied this and talked about how different scenarios of the same reaction would affect their delta T's, their Q's, or their delta H's and things like that. And so something that you'll definitely want to revise later on to kind of more thoroughly go into this calorimetry and the application of calorimetry and solving for delta H and things like that. But I'm not going to go into that detail in the Get to Know Your Data booklet. I just want to focus on the equations that are provided to you here. Questions?
Mr. Trong.
Yeah.
So I'm trying to clarify the units after when it says grams parentheses. That's joules to grams to the negative first, and is that Celsius to the negative first as well?
Yes.
Okay. And the Celsius to the negative first can also be replaced with Kelvin, right?
Correct. Right, Alexander. Yeah.
Right. Thank you.
No problem. Okay. Other questions?
If they give you the specific heat capacity, kilojoules per kilogram, do you have to change anything?
That's a good question, Alejandro. No, because the value in kilojoules per kilogram is the same as the value in joules per gram, because the ratio is both 1,000 to 1,000, so they cancel each other out.
Just wanted to make sure.
Yeah.
Thanks.
Now, I don't think the IB would do this, but theoretically, if they gave it to you in kilojoules per gram, then you may have to like finagle some units and things like that. But again, this is why I stress writing your units out so much, because I would say 50% of the mark students lose on correct like understanding is units. Just not keeping track of their units. They write, oh, here's my answer in kilojoules when it's really in joules, or here's my answer in centimeters cubed instead of decimeters cubed. And so you'd be surprised how many marks students can miss from not paying attention to the units. Okay. Acids and bases for SL is fairly straightforward. It has to do mostly with the calculation of delta H. Sorry, not delta H. For pH with strong acids and bases. So it's fairly straightforward in this concept. And you have to remember that lowercase p is equal to negative log. No matter what you're talking about, whether you're talking about POH, pH, pKa, pKb, pKw, all of that, actually, you know what, I would probably say that this stuff is actually higher level in here. But lowercase p in IB chemistry always means negative log. Okay, that's why I don't like the lowercase p in the PV equals nRT, because I think that's misleading, because it's not really lowercase p, it's not negative log, it's something else. And so here we're looking at these ideas. Now these are the same. Okay, H3O plus and H plus are the same idea. Sorry, they are the same concept for all intents and purposes. And so you will use these interchangeably. Now, you got to really make sure that you're careful when things dissociate, like strong acids. Some of them dissociate twice as much molarity, so you have to recalculate the molarity of H plus based on your original molarity and things like that. And also, I would know that pH plus POH equals 14 for standard level. Okay? For higher level, that 14 could change based on the temperature of the water, and that's something we'll review in the topic 8 lesson in a separate Saturday session. Also, you want to make sure that you understand acidic means your H3O plus is greater than your OH minus, and neutral is when they're the same. It doesn't always mean 7. In standard level, it may mean 7 because you're only at 25 degrees Celsius all the time. But for HL, especially, when the temperature changes, neutral changes as well, because it dissociates more, so the pH of neutral actually goes down for this. And so does the POH. They both go down. Okay. Okay. Questions about that? Now, going into the higher level equations, the first one here is the energy of a photon. And this is related to the 2.2 equation that SL used, but now we're using energy is equal to Planck's constant times frequency. Okay. And so you're given Planck's constant in the next table, so you don't need to memorize that. And Planck's constant is joules times seconds. And frequency is seconds to the negative 1, so therefore your energy should be in joules here. So the frequency of a photon is directly related to its energy. The higher the frequency, the higher the energy. The higher the frequency, the shorter the wavelength. So you could also say the shorter the wavelength, the higher energy as well, in kind of a transitive property manner in this case. Now, 15.2 is a big equation. This is the main delta G equation, okay? And this is Gibbs free energy. Okay. And this is delta G is equal to enthalpy minus temperature times entropy. Okay. So it's the enthalpy value minus temperature times the entropy. And you want delta G to be less than or equal to 0 to be considered spontaneous, that it reacts on its own. But you have to be careful. Again, what they don't tell you is if you're not paying attention very closely, the units of enthalpy and entropy are generally different. Enthalpy is usually in kilojoules, temperature is in Kelvin, but entropy is in joules per Kelvin, because entropy is a much smaller value than enthalpy. And so paying attention to that is really key here, because usually you have to convert one of the values so that the units can match, because you can't subtract units that are not the same, the equivalent. And so enthalpy is in kilojoules, but entropy is in joules. Usually what I do is I divide this one by this side by 1,000, so I get my answer in kilojoules, and that's what my delta G is in. But again, telling you just enough to remind you of what it is, but not enough that any student could just look at that equation, plug in values, and get it right. Units are extremely important. And you also use this to predict spontaneity. One of the things that we talked about in topic 15 was if you apply signs to delta H and delta S, you can determine what the sign of delta G will be. It sometimes will be always positive, sometimes it'll be always negative, and sometimes it'll be sometimes negative based on temperature. And so instead of memorizing this whole grid, like this X and Y axis of like this side is sometimes always never, like always high temperature, never low temperature and stuff like that, just use this equation and plug in the signs as you need it. So like if delta H is negative and delta S is positive, well, that's a negative minus a positive, which is always negative. Well, if delta H is negative and delta S is negative, now it's a negative minus a negative, which is a positive. So therefore, you want T to be as low as possible so that the negative stays there. And so applying these ideas is really, really important. Questions about that? Okay. These next three equations we're not going to talk about right now because they, as you can see, are topic 16, which we have not talked about yet in class. But they're actually all the same equation, just rewritten in different manners. And so these are activation energy, calculations. So you can use any form of this equation to be able to solve for the activation energy. It's kind of like different forms of the same function in math. There's like there's a slope equation or like a standard equation and things like that. And so each of these equations have their own purpose, but they're all able to be used at any given time. So don't overthink this too much, but we'll analyze each of these equations later on. So don't worry about those three equations right now. This one is your delta G relative to, proportional to, equilibrium. Okay, and so now you're dealing with the K constant, your equilibrium constant here. And R being the gas law constant and T being the temperature in Kelvin. Now, actually, that looks like an infinity sign. I wanted more of a proportional sign. Sorry. And understanding that to get delta G to be negative, natural log of K has to be positive. So you want K to be greater than 1 for delta G to be less than or equal to 1. Because when you take the natural log of a number greater than 1, you get a positive value. And that positive value will then carry on through your positive R and positive T to get a negative value overall. So understanding how you plug in K in there to solve that. This is delta G proportional to cell potential. Same idea, but here you want E to be greater than or equal to 0. That way your N, your F are both positive, and then your E is positive, so therefore you get a negative value overall. You also need to remember that N is the moles of electrons canceled, when you're balancing reactions and you cancel out a number of electrons to combine them, that coefficient goes in as n. So it could be 1, it could be 2, it could be 5, it could be 10, or whatever. Excuse me, it could be any of those values. F is Faraday's constant, which is also given to you in the next table as well. Questions about that? Okay. Here's the good news. Everyone can cross out all of these equations after that. Anything that starts with a letter, that's optional material. So we're not doing an option this year, so you don't have to worry about any of that. You can cross out all of this stuff here as well.
Wait, Mr. Ron, can you scroll up again? 1 second. 1 second. Here. Okay, good. You can scroll down again. Thank you.
No problem. So you can cross out all that material from A to D. You don't need to know any of that material.
Wait, Mr. Strong.
Yeah, Moritz.
You know those last couple of equations? Are those going to be the ones that we cover in class after break?
Wait, which ones? Oh.
Like the delta G ones? And
No,
the
no.
K ones?
No, we did those.
We did?
Yeah, in topic 7 and 17, the first topic, equilibrium, we did talk about that very briefly and how that applied. And then topic 19, we plugged that in also. Yeah. The ones we'll talk about are the 16.2 equations. That's a topic that we haven't covered yet. Yeah, I mean, we'll revise that on a Saturday session, but yeah, we have talked about those briefly already. Okay. So this is the table of values that the IB deems important enough to give you the values to prevent you from making mistakes and mixing them up and things like that. And so Avogadro's constant is converting particles. Okay. From moles. And so if you have a mole of a substance, you have to figure out how many particles there are, and then you may have to figure out how many atoms are in that molecule as well. And so you're going to use 6.02 times 10 to the 23rd. Particles equals 1 mole. Or units, I guess, whatever way you want to think about it. Now, if you notice that all these values that IB gives you have 3 significant figures. And so that's pretty a good constant kind of understanding that most of your answers will need to be in 3 significant figures to maintain the threshold of acceptable values. And so 3 significant figures is always a fail-safe. Now, if the question asks you to answer with the exact number of significant figures, then you may want to look at your values and decide which one it's going to be. But for almost always, 3 significant figures will be sufficient for your overall answer to be within the threshold of the mark scheme.
Do you assume that these values are exact? So like if they want you to answer with 4, you just assume that these are 0, 0, 0 forever?
No, you do not. So yeah, you will assume these are not exact values. So they have 3 significant figures. They can be the limiting factor in your significant figures every time. Okay, that's a good question. Okay, gas constant. We see the gas constant used in, like we said before, PV equals nRT. For a higher level, you see it as in delta G is equal to negative RT ln K. So it's 8.31 joules per Kelvin mole. Okay, this is different than SAT2. This is different than AP chemistry, where they use 0.0821 liters times atmospheres per mole Kelvin. So just be aware that the constant is different, but this is the one that we've used for the last 3 years of chemistry. Another kind of tricky thing is STP is 22.7 decimeters cubed per mole. Okay, because the IB has changed its standard temperature and pressure to simplify things for you. And so it's not 22.4 anymore, it's 22.7 when you plug in the new standard temperature and pressure values for gases. So it's 22.7. Make sure you reference that. Also, again, conversions. There's no excuse for not knowing how many centimeters cubed are in a decimeter or how many decimeters cubed are in a meter cubed, because they literally give you this calculation right here. There's 1,000 centimeters cubed in decimeter cubed, and there's 1,000 decimeters cubed in a meter cubed. For gases, liquids, whatever, that's your conversion. So you should always have at your availability that 1 decimeter cubed is 1 times 10 to the third centimeters cubed. Okay. Here's what I was talking about with standard temperature and pressure. Of gases. It's now 100 kilopascals and not 101.3, which is 1 atmosphere. And that's why the small subtle change in 22.4 to 22.7 occurs, because your pressure is decreased a little bit, so your volume is going to naturally increase a little bit at the same 1 mole of gas. SATP is standard ambient temperature pressure, which is what you usually use in energetics. Like when you're using delta G or delta H or delta S and stuff like that, that's the standard conditions for that. Still 100 kilopascals, but now you notice it's at 25 degrees Celsius. Excuse me. As opposed to 0 degrees Celsius as it is with gases. Questions about any of that? Okay. Your speed of light value is going to be in your C is equal to lambda nu, which is your wavelength, times frequency equation. I think that's the only place you would use it, because I guess you would use it in nuclear chemistry as well, but that's in the option. So that's the only time you're going to be using it. And notice again, the units are important. Meters per second, which means your wavelength has to be in meters, or your frequency has to be in seconds to the -1, or hertz. Same thing. A hertz is equal to seconds to the -1, but I feel like the IB would write it in seconds to the -1 just to avoid any confusion. Specific heat capacity, like Alejandro was asking earlier, kilojoules per kilogram gets you the same quantity as joules per gram because the ratio is the same. They wrote it in Kelvin here, which is fine. They can write in degrees Celsius, which is fine also. So it doesn't matter. I know in physics, I think you use like 4,180 joules per kilogram because you're dealing with much larger quantities than you do in chemistry. Now, having said that these values are all given to you in the data booklet for paper 2, there are times that multiple choice questions will ask you about these. Like I've literally seen a question just say, what's the specific heat capacity of water in the correct units? And so you'd have to comb through all the choices and see which one reflects the specific heat capacity of water with the right units. Or they'll be like, what are standard temperature and pressure conditions? So it sounds very easy, but don't take it for granted that you don't need to know these values just because they're giving you data booklet, because in paper 1, they could still test you on these values. So don't not memorize them because they're in your data booklet. I would still be very familiar with them to at least be able to answer a multiple choice question.
What happens if a multiple choice question wants you to calculate the enthalpy of a problem? Would it give you the equation or no?
Uh, that's a good question, Alejandro. Usually, no, they don't. But usually, what they'll do is like a lot of times because you don't have a calculator on paper one. What they'll do is the answer choices will be the setup of the problem. So you'll be able to kind of see based on the setups of the problems what the equation is. Like instead of like writing the answer of Q equals mc delta T, they'll have like the mass times the specific heat times temperature, like as a setup without calculating it to see if you still get the right answer. And so that's a good question. I don't think there's a lot of math on it on the on paper one because you have no calculator. So I think you're less likely to have to calculate it, but more likely to just be able to identify the correct setup for solving the problem.
Okay, thank you.
You're welcome. Planck's constant, like I said before, 6.63 times 10 negative 34th, is in your energy of a photon equation to figure out, once you know the frequency of a photon, what the energy of that photon is. Faraday's constant, that's used in delta G is equal to NFE. And electroplating. Because don't forget, this is per mole of electron. So 96,500 coulombs per 1 mole of electrons determines, based on how much current you put through a solution, how much metal you could expect to electroplate. Yeah, these last 4 equations are HL. Ionic product constant of water, Kw is 1.00 times 10 negative 14. This goes back to kind of reinforce the idea for a higher level that H plus times OH minus equals pKw. So if I want to find the pH at a different temperature than 25 degrees Celsius, these values are the same when they're neutral. So then that would be equal to, not pKw, I'm sorry, not pKw, just Kw. So it would be x squared is equal to Kw, so x would equal to the natural log of Kw. I mean, sorry, natural log, square root of Kw. So if you wanted to solve for the pH of neutral at any given temperature with a given Kw, you could do that using this equation here. Now, they give you all the Kws at other temperatures in the later on the data booklet we'll see in part 2, but know that that idea is still possible. Now, I think this last calculation here, I don't think you need, because I think you usually use that for like nuclear energy and mass defects to calculate how much like energy decay gives off, but that's not part of your core curriculum, so I don't think you need to know that. Okay. Questions about any of that? The electromagnetic spectrum, okay? This one, it's kind of hard to tell exactly what the IB kind of recognizes as SL versus HL, but you want to know a few things, okay? That gamma rays over here are the highest energy with the shortest wavelength and the highest frequency. Then comes X-rays, and then UV, and then violet, all the way down to red, and then IR. And so the way I remember it is that UV is really high energy, IR is low energy. So the visible spectrum fits in right between there, going from violet to red. And so violet has the shortest wavelength, and red has the highest wavelength because violet has the highest frequency, and red has the lowest frequency. This might be a multiple choice question where the IB asks you to rank the following photons of radiation in energy order, things like that. Or maybe the IB gives you like a frequency and asks you to solve for the wavelength and then identify what type of radiation it is. So you kind of look at these exponents here to kind of predict what type of radiation it is on the electromagnetic spectrum. So that's the only way I could think about you using this this table here, ranking the energy or the wavelength or frequency of different radiation, or applying calculations that you already did to figure out what type of radiation it is giving off. Okay. Questions?
Nanometers are 10 to the 9th meters, right?
Yes. So 1 nanometer is 10 to the negative 9th meters. Correct. I don't think we use angstroms in here, which is 10 to the negative 10th, so I think that's more of a physics thing. Okay. And I feel like the IB would give that to you if you needed it for a calculation, but I guess you don't want to assume, so I would still know that in the kind of back of your head. Now, I'll admit, I'm not sure exactly why they show you this table. The only thing that I can think of really here is that understanding that a proton weighs about 1 AMU, a neutron weighs 1 AMU, an electron is negligible because it's like 1/1840th of a proton. So when you're doing mass numbers, they're always whole numbers because you're just adding the protons and neutrons together. You're just kind of ignoring the electrons because they're so much smaller in mass that they don't have a significant impact on it. So I still haven't seen a lot of like problems where this is being used, but this might also reference the option as well. So don't worry too much about this table here. The next 2 pages are names, symbols, and atomic numbers of common or all the elements on periodic table. Now, sometimes when the IB gives you a difficult or an uncommon element, they will say Z equals, and that's your atomic number. So if they say Z equals 66, what they mean is that it's dysprosium, so that way you don't have to hunt for what dy is on the periodic table. They're saying, oh, look at number 66, because that's what that is. I think with this, it's just some of y'all assume you know what the symbol for elements are and you make mistakes about it. And so some of them sound a little bit sillier than others, but things like sodium and sulfur, potassium and phosphorus, copper and cobalt, okay, argon versus arsenic, silver versus gold. Oh, another popular one. Magnesium versus manganese. Okay. So please make sure you get the right element, and please make sure that you're looking up this so that way you don't get molar masses wrong for compounds or come up with the wrong charge for the formula and things like that. Just make sure you have the right one, and just be careful. You've got plenty of time. Be very deliberate about going, okay, I'm looking for potassium. I'm looking for number 19 here. Or sodium is number 11, whatever. But make sure that you are deliberate about this so you don't mix things up here. I think that's why they give you the table, to avoid any of these kind of mix-ups here. Questions about that? Okay. So that goes through these tables here. Now, this is periodic table number 1. And there are 4 periodic tables provided you in successive order in this data booklet, and each of them tell you a different amount of information here. Okay. Now, the first thing we're going to do is this. I'm going to label some very common groups names that you need to be familiar with for these. Okay. For example, this first one is the alkali metals. This is the alkaline earth metals. This section here is the rare earth metals. Now, these sections here go in after lanthanum and actinium in the actual periodic table. If they were actually to fit where they belong, the periodic table would be twice as long. So scientists decided to make them an addendum to the periodic table to minimize the width of the periodic table so that it was more usable. So if you look at the atomic numbers, they fit in right there. Cerium and thorium fit in right after lanthanum and actinium. '17, halogens, and 18 are the noble gases. So be familiar with each of these major groups that I've labeled here, because the IB might reference them.
Do we have to know anything like transition metals or no?
Yeah, I mean, I guess you could group in the section of transition metals here as a whole. But in HL, you'll talk about more specifically about that section of properties and things like that you normally wouldn't talk about in standard level. So I would know where they are, but the properties and stuff like that are more specialized to HL material. Okay. Yeah, I'll put it right here. Okay. Now, like this table says, the atomic number the element symbol and the relative atomic mass in AMUs. So what this value underneath the symbol is twofold. One, it's the average mass of one element atom of that substance in AMUs, or it's the mass in grams of 1 mole of that substance. But regardless, they're both the same number. Okay, so you don't have to worry about manipulating the number. That number is constant. So the average carbon atom weighs 12.01 AMUs, but then 1 mole of carbon weighs 12.01 grams. The only thing you want to remember is that no one atom has a decimal point value. They're all whole numbers. So if I ask you how many carbon atoms in a sample have a mass of 12.01, you say 0. Because no atom individually has a mass of that. That 0.01 originates from the average of the two or more different isotopes that a substance has. And that's where you calculate that value here, which is, the way I like to do is this. I do percent abundance times mass times percent abundance times mass 2, percent abundance times mass 3 over 100. Instead of trying to convert my percentages into decimals and then multiplying, I let the dividing by 100 do all the work. Because I think sometimes students have trouble converting percentages. Sometimes they move the decimal point different number of amounts, too many to the left or not enough to the left. And other times they'll see a decimal percentage and then they won't change it to a decimal, and then it'll be all messed up. It's like they'll see 0.5%. It's like, oh, it's already a decimal, I don't need to change it. But really it's 0.005%. And that throws off all their calculations, things like that. But one of the tips that you should think about is your average mass should be between mass 1 and mass 3. There's no way you get an average outside of those two maximums and minimums by adding these values together. So if you get a mass that's less than mass 1, you did something wrong. Whether it's a calculator error, whether it's you writing something down, whether you read something wrong, that should be a dead tip off. And that average mass should be between the highest and lowest values, and also should favor the value that's in greatest abundance. Hence, if you look at carbon, it's 12.01. That means the isotope of carbon 12 is in the most abundance in a sample, any sample of carbon. Other times, you might have this. Like, they give you an element, they tell you, I have two isotopes of that element. Using the periodic table, what's the percentage abundance of each of them? And so, like, for like example, like gallium is 69.72, and let's say there was a 69 gallium and there's a 70 gallium. Well, what's the percent abundance of each one? Well, here you'd have the percent 1 is equal to x and the percent 2 is equal to y, but x plus y must equal 100. So therefore, you can set y is equal to 100 minus x so that you can use a system of equations to figure out the percentages here. Questions about that? Okay. Give you all a chance to write that down for a second. So you may have to do some average atomic mass calculations or relative atomic mass calculations as well. Okay. Periodic table number 2. And this has to do with melting and boiling points of elements in their standard state. And so what you'll see here is your melting point and your boiling point of every single element provided in that box. Now, there's only two things that I think that this table actually helps you with. One, it's to determine the standard state of an element. Meaning, like, what phase of matter is in it? Is it a solid, liquid, or gas at STP? And the way I think about this is I think of it like a number line. Where if it's less than negative 219.7, it's a solid. If it's in between the two values, it's liquid. And if it's up here above negative 188.1, it's a gas. So what I ask myself is, where does 25 fit on this number line? And 25 fits in this, on this side of the number line. So therefore, fluorine is a gas at room temperature, at standard temperature and pressure. I guess standard ambient temperature and pressure for our purposes here. So you can kind of see the melting point and boiling point of a variety of different elements here. Another thing you might point out is that carbon and silicon, even though they're nonmetals, have very, very, very high melting point and boiling points because they are giant network covalent molecules, meaning that they don't have weak intermolecular forces holding them together. They're all covalent bonds. So therefore, the amount of energy it takes to break those bonds to melt or vaporize it is very, very high. So carbon and silicon tend to kind of be exceptions to the rule of nonmetals being gases at room temperature because of how it's structured. The other thing you might do is talk about, oops, sorry, not blue, like the trend of melting and boiling points in a group, like fluorine versus chlorine versus bromine versus iodine. And if you look, 25 degrees Celsius makes fluorine a gas, chlorine a gas, bromine 25 is in between those two values, so it's a liquid, and iodine 25 is below the lowest number, so it's a solid. So it increases IMFs as you go down. And that's because the greater mass makes the attractive forces stronger, which then allows things to solidify. And this has to do with covalent molecules. Conversely, if you look at metals, you'll notice that they decrease as they go down. Now, they're all still solid, but they decrease as they go down for the most part. So you'll see like lithium, melts at 180.5. Sodium melts at 97.79. Potassium is 63.38. Rubidium is 39.30. Cesium is 28.44. Now, that is because metallic bonding depends on your cations and delocalized electrons. Okay. And so you want smaller cations to be stronger metallic bonding because you want the cations to be smaller so they're surrounding more around with electrons to create a stronger attraction there. So that's why lithium has a higher melting point than cesium because the cations are actually smaller. You'll also see that the metallic bonding increases as you go across because the charge of the cation also strengthens it. So the higher the cation charge, the stronger the attractive force is. Notice that beryllium versus lithium. Beryllium's a 2+, lithium's a 1+, and there's a significant difference between the melting points in those two substances. So that's another thing to think about as well. Periodic table number 3. Okay. Now this is more the periodic trends one. And so you'll have ionization energy. And I'm changing color here on purpose. Electron affinity for higher level. And then electronegativity is back to standard level. Okay. So in each of the corners, they have different values here. So in the top left, there's first ionization energy. I should write first ionization energy here. In the top right, they have electron affinity. And if there's 2 of them, they have that. In the bottom center, they have electronegativity. And we're going to talk about each of those things and what they mean here for your understanding. Okay. What does first ionization energy mean? Okay. First ionization energy is the energy required to lose the first electron from an atom in its gaseous state. So transforming X into X positive is first ionization energy. Oops. Second IE would be going from positive to 2 positive. Notice that you're not combining the reactions, they're consecutive. And so second ionization isn't X to X2 plus, it's only X plus to X2 plus, and the first is X to X plus. So keep them all separated, because for a higher level, you'll have to apply this concept in the Boron-Haber cycle and figuring out those calculations. So keep those ideas separate. And that's a common multiple choice question, is like, which of the following shows the first ionization energy of aluminum? So you'd want Al gas yields Al plus 1 gas plus electron. Okay. Electron affinity for higher level is the energy it takes or released when an atom gains an electron to become a negative ion. Okay, and those values are provided to you in this, excuse me, in case you need to use them for the Boron-Haber cycle. So keep that in mind for this. Okay. Electronegativity is the attraction a positively charged nucleus has for a shared pair of electrons. So essentially, how much does that atom pull on the bonded electrons toward itself? How strong is that pull? So this is all relative. And we use the Pauling scale in IB, which is at 0.7 to 4.0 that we're used to, finding the difference in those values to figure out what type of bonding there is that's present in the structure here. questions about any of these three terms here while people are writing stuff down? Okay. Now, here's the thing. Because these values are all given to you, the IB is never going to ask you what happens to the ionization energy as you go across the periodic table, because guess what? The values are already given to you. So anyone can read numbers off a table, so why would they ask you about that? What they're going to ask you about is why the trends occur. Why is ionization energy increasing as you go across? Why is it decreasing as you go down? And so that has to do with more atomic structure aspects. And so explaining why is really the key to getting marks on these types of questions. So as you go across a period, you want to establish a couple things to be able to compare elements in the same period. One, same energy levels. So they have the same number of energy levels in a period. Two, increased nuclear charge. The addition of that one proton as you go from left to right on the periodic table creates a stronger attraction with the nucleus for the outermost electrons. Now it's not 1-to-1, it's just a stronger overall attraction. Okay. So stronger overall attraction. Okay. So that's why ionization energy increases as you go across, because the stronger attraction means there's more energy that's required to remove an electron. So it's about these explanations that help you state why the ionization energy goes across. It's not enough to say, oh, it increases as it goes across, because that's already obvious based on the periodic table. It's about why that is the case. And as you go down a group, now you have the same nuclear charge, essentially, and you have an increase in energy levels, which increases shielding. Okay, now when you increase shielding, then there is a weaker attraction. Because shielding is the inner electrons inside an atom. And the more inner electrons you have between the nucleus and the valence electrons, the more that attraction is being kind of deflected or contained before it reaches the valence electrons. So the attraction is actually weaker for the nucleus to the outermost. That's why the ionization energy goes down, because the more inner shells you have, the weaker the attraction, the less energy it takes to remove an electron. Let me leave that here. Questions? Now, there's one thing I want to talk about here, and that is exceptions to trends. and this is the one thing that the IB might kind of catch you on, is yes, the general trend applies for most elements, but across a period, there's sometimes exceptions to that rule. And most of these involve orbital diagrams. So if you're trying to figure out why an element doesn't behave the way it's predicted to behave, it's usually because of the way the electrons are oriented in their orbital diagram. So for example, nitrogen versus oxygen. It turns out, even though oxygen's to the right of nitrogen, it has a lower first ionization energy than nitrogen. So why is that? The reason why is because oxygen has an additional electron in its 2p orbital, which means that when it loses it, it becomes half filled. So there's actually an energy incentive for oxygen to lose its first electron versus nitrogen, which already has a half filled sublevel. So it's a fairly stable, and to lose an electron would actually make it more unstable. So therefore, it takes more energy for that to occur. So a lot of these trend exceptions have to do with that concept here of how are the electrons arranged. For example, beryllium versus boron is another common example. Beryllium being this, and boron being this. Well, boron is able to more easily lose its electron to empty out a 2p sublevel than beryllium is to lose one from an already full 2s. And so you see that difference here when you look at beryllium's ionization energy level versus ionization energy versus boron's. This one's 900 and this one's 801, even though according to our general trend, boron should be higher. So anytime you have exceptions, I say go to electron configuration, see what's weird or what's unique about this scenario, and then try to explain it using that. Because that's where most of the exceptions to any energy stability lie, is how are the electrons distributed in their energy levels, and what benefit does an atom have for losing or gaining this electron that it normally wouldn't have, according to our general trend. Okay. Questions? Okay. Last periodic table. Okay. This has to do with atomic ionic radii and common ionic charges. So this table is either A, used for comparing the size of radii and stuff like that, or B, identifying what the common charges of these ions are so that we can use them to make formulas. Notice here that like tin and lead have multiple oxidation numbers of 2 plus and 4 plus. Copper is 1 plus and 2 plus. Cobalt is 2 plus and 3 plus. Things like that. So this is your kind of one-stop place to find out these common charges and these common values for each of these elements in their ionic state. Okay. Now, the first thing you want to kind of be familiar with is comparing ions. And a common one they like to compare is P versus S here. And it's tricky because the IB gives P as 5 plus instead of 3 minus, so it's not as predictable as usual. P is 5 plus, which has a radius of 38. S has a 2 minus, which has a radius of 184. And they might ask, state and explain the significant difference in ionic radii between phosphorus and sulfur. And what that really comes down to is, well, how many energy levels of electrons do you have? Phosphorus having 15 protons and only 10 electrons versus sulfur having 16 protons and 18 electrons. So notice the significant difference in energy level. Sulfur has one whole energy level above what phosphorus is, according to this table. So therefore, that should be a significant difference in the ions. But usually what the IB does is it talks about isoelectronic species, where the electrons are the same amount, but now your protons are different. So you might compare something like, I don't know, O, Ne, and F. F1 minus, O2 minus. So O2 minus is 140, Ne, actually, hold on a second. That's kind of significant, but it's okay. 133 and then 62 here for Ne. Now, to explain this, what we have to look at is they all have 10 electrons. They all have 10 electrons because oxygen has 8 normally, gains 2, that's 10. Neon always has 10. Fluorine has 9, gains 1, that's 10. So the difference really here is the protons. Oxygen only has 8 protons. Neon has 9. Fluorine has 10. So the more protons you have for the same number of electrons, the more attraction there is, the more tightly the atom can be pulled in. So neon is smaller than F, which is smaller than O2 minus because of the number of protons here, which creates a greater attraction. So that's a really important kind of concept here of isoelectronic species and comparing them. They might do this on the multiple choice instead of the short answer, but it is something that the IB can ask about here. So whenever you're comparing atomic or ionic radii, first thing you want to write down is number of protons and number of electrons each species has, and that's a good starting point for you to compare between those two things. Questions? Okay. Covalent bond lengths. Okay. I think this table is a little bit extraneous. Like, I don't know, like, where I haven't seen a lot of times when they use this, but here's what I'm thinking for this idea is covalent bond lengths relate to covalent bond strength. So the longer the bond, the weaker the bond strength is. Now, this is a cross table, so the way you read it is to find the intersection between the two spaces. So, for example, carbon and carbon has a bond length of 154 here. Let's see, iodine to iodine has a bond length of 167. So reading the chart here is kind of important, but you're not using these values to calculate anything. You're not using these values to like quantify anything. You're just kind of comparing values to show the concepts here. Now, key thing here is these are all single bonds. The other bonds here, the multiple bonds are at the bottom. So things like N2 or O2, those diatomics, their bonding is actually at the bottom. N triple bond N versus O double bond O, things like that. Benzene, resonance structure, those ideas as well. And so correlating the bond strength with bond length is the concept of this table. I think this table is a little bit extra. You won't use this very often unless you're trying to state and explain an idea where you have to cite the values for this. Now, keep in mind this, and I haven't said this yet, but if a problem says refer to table so-and-so to help you explain, you need to make sure that you cite values from that table to do this. And so they might say, referring to table 10, state and explain the difference in bond length of O to O single bond and O to O double bond. To get full credit, you would have to say that O to O single bond is 148 and O to O double bond is 121. So citing that value shows that you actually went to the data booklet and looked at those values. So keep that in mind. If they mention a table in your question, anywhere in your data in your IB exam, take values from that table and put them in your answer, because that shows you that shows the IB that you referenced the table as requested. And a lot of times that's what will get you full marks versus partial marks, is saying, oh, student cites value as 148 and 121 respectively. That's 1 mark. So make sure that you're using this table in your explanations here.
Could I ask you about benzene really quickly?
Yeah, sure. Yeah.
Is that double bond like length the length of every carbon to carbon bond in a benzene, or just the double bond length? 'Cause
No.
it's
Oh, yeah, it's resonance. You're right, Alejandro. So this is every bond, and that's, you can't see it here, but it's a dashed line. So what they're actually saying is that this is like what one of the bonds looks like in benzene. So if you did like this, oops, that's the same thing, isn't it? The dotted line represents the delocalized bond that goes around. So each of these bond lengths is the same.
Thank you. I didn't realize it was dotted.
Yeah, it's really hard to see on here. But so, yeah, the dotted line here represents the resonance. And that's what makes it a regular hexagon. That's why the hexagon shape is exactly like regular, because each of those bonds is the same. You know, that's what, I think we were talking about this before, that if there was no such thing as resonance here, then you would have this weird shaped structure here. Something like this, right? Because your single bonds would be longer than your double bonds, and so you would have this really uneven structure. And scientists have found that that's not the case, and this is what explains resonance. So that's a good point. And this has a bond order of 1.5, meaning it's about 1.5 of a bond's value here, which tells you the bond length should be in between a double bond, which is 134, and a single bond, which is 154, which 140 is. It's not dead in the middle, but it's somewhere in between. Okay, other questions? I think the common question they ask about here is ozone. Because ozone, if you remember, has resonance as well. And so its bond strength is somewhere in between a double bond and in between a single bond. So if a single bond O is 148 and a double bond O is 121, you could estimate that the bond length here is about 130, maybe 126. They would probably just say student gets awarded the correct mark if his or her value is in between 121 and 148. So it doesn't have to be exact. There'd be a range of acceptable values.
So would the value for C double bond C in benzene be the one for all like carbon resonance structures, basically?
Ooh. No, I think the length would vary just a little bit, Moritz, if you had resonance in like a long chain or something like that. But for our purposes, for IB chemistry, benzene's the only version of that we have to do.
All right, thank you.
You're welcome. Okay. Hit the home stretch for today. This is the last page that we're going to do today, and then we'll finish the rest of it tomorrow. Hopefully, tomorrow won't take 2 hours either. We'll be able to finish a little bit early. Okay. Bond enthalpies and average bond enthalpies here. Now, it seems silly to say both those things, but in actuality, they are two kind of technically different things. A bond enthalpy is an absolute bond enthalpy, meaning that there's only one form in which this bond ever occurs. So, for example, F2, the FF bond only exists in F2, and that's the only time it ever exists. Okay? There's no other stable bond that exists with an F to F single bond. So that's absolute because it is the only version of that bond that's possible. So you get a value for that, and that's the exact value it takes to break that bond. The problem is many bonds don't fit that requirement, meaning they have a lot of different scenarios in which that bond exists. For example, the C to H bond. The C to H bond exists in a lot of different structures, from methane all the way up to like decane or something like that, right? There are all these C to H bonds that are all different, and so we come up with an average for that. And this is how they do that. So what they'll do is they'll take something like CH4, and they'll break all the bonds in it. So you'll end up with C and 4 H's. And that will take a certain amount of energy, because you can't individually break bonds in a substance. You either break all of them or you break none of them. So they break all of them so they can get an exact answer. And they take this delta H and we divide it by the 4 bonds to get average bond enthalpy. So we break all 4 bonds, even though each of them take a different amount of energy. We break all 4 of them, and we average how much energy it takes to break each of those bonds. And that's what average bond enthalpy is. So you break all the bonds, you divide by the number of bonds you broke, and that's your average. So yes, maybe the first CH bond is a little bit less, and the last CH bond is a little bit more, but we just care about an average here because we are using this for a lot of different structures here. So it's not going to be always precise. It's always going to be slightly off. Now, having said that, while this is how you calculate it, the bond enthalpy itself would be represented by this. Because the bond enthalpy is only breaking one bond. So this value here really relates to what this is, assuming that you're saying you're breaking one CH bond and you're leaving the rest of the molecule together. So when you take the delta H of the red and divide by 4, that's what that equation is saying. So there's a difference between the red and the orange here. Okay. Questions about that? Now, there's a table here with single bonds and double bonds and multiple bonds. Obviously, there are some common ones that you really need to know. C to C single bond, really, really common. Okay. C to H bond, obviously also very, very common. Okay. H to H bond, really common. And H to O bond, really common. A lot, especially in these combustion reactions and things like that. So some of these values are ones that you do need to be able to pick out very quickly from the table itself. Now, having said that, a lot of the other multiple bonds you have to really be careful about. O2 is here. This CO is the double bond of C to O and CO2. Here's N2. A lot of students use the N single bond N when they're doing the calculation and you get it wrong if you do that way. And you'll lose 50 to 75% of your marks when you get one side of the equation wrong. So it's really, really important that you do all of it correctly, because you get penalized significantly for making one mistake on these type of problems. And then C to C double bond, C to C triple bond as well in here. Now, the way I do it to prevent mistakes, that I find is the best way to do it, is to manually draw out all the bonds in all the structures to try to prevent mistakes. Okay, so for example, let's say I have C2H4 plus O2 yields CO2 plus H2O. And I have something like this. I draw out all my bonds to make sure I count them up correctly. So because you wouldn't believe how many times kids mess up the amount of HO bonds or amount of C double bond O's in here, because they just look at the coefficient and they just multiply the coefficient by the bond and forget that there's 2 of that bond in CO2 and there's 2 of that bond in water. And that throws off the entire side of your calculation, which means you're going to lose a lot of marks on that problem. So I draw out all my bonds here to make sure that I have all the right number of bonds here. And so my left side is 1 C to C double bond plus 4 C to H bonds plus 3 O double bond O's. And on the right side, I have 4 C double bond O's plus 4 O to H bonds. And these bonds are breaking, and these bonds are forming. So this is endothermic, and this is exothermic. And the values given to you in your data booklet, like right above me, are all positive. So they're all endothermic. So this side is going to stay that sign. And this side is going to be negative. And then you combine those two values together to get your enthalpy of the reaction. So this is one of those situations where it's reactants minus products. If you don't want to change the sign of bond enthalpy, then it's reactants minus products. But if you want to change the sign of bond enthalpy, you make the products negative because you're releasing energy, and then just add the two values together. Just don't do both, right? It should be a tip-off that a combustion reaction should always get you a negative value. So if your sign gets you a positive, then you did something wrong. You probably did it backwards, to be honest with you. Questions about that? Okay. That's the end of part 1's lesson on Get to Know Your Data Booklet. The rest of it we will talk about is enthalpy, entropy, and Gibbs free energy, moving on to equilibrium and acid-base and electrochemistry, redox reactions, and organic, and that'll be the entirety of the data booklet. And so we'll finish that in part 2. So let me stop recording right now.